So this discussion is going to focus on the study of kinetics. So before we get into really getting in depth in kinetics, we're going to kind of go back and just review something that we already kind of talked about. We looked at motion and just kind of talk about, kind of go back and review some of the concepts just related strictly to motion. So there are basically a few things that determine motion, okay? So in looking at, and again, we'll relate it to the, something as simple as this picture that we're looking at of a sprinter, okay? Okay, so things that determine motion. Number one, the type of motion, okay? So we know we have translatory and rotary motion, okay? Remember that from our previous talk, okay? Translatory motion is when all the points on one body move from point A to point B. It's that linear motion. Whereas rotary motion is when something moves about an axis. And in that case, not every part of the moving body is going to be going at the same speed. When we look at this picture, we see a combination of things. Okay, we see translatory motion. We see the runner running and changing his whole body position. But in order to get there, he's using rotary motion. Okay, he's using rotary motion about his ankles, knees, hips, arms. In the case of running, the arms are important. So we have that. We have the location that motion is taking place, and that strictly just refers to the planes and axes of motion. So again, if we look at this picture, okay, we look at the primary motions that are occurring. Okay, so for instance, hip flexion, hip extension. Those occur in the sagittal plane about the frontal axis. Okay, that's the way we would describe part of that motion. We look at the magnitude of motion, okay, and all that looks is the distance and how, for instance, distance would be how far a force moves a body, okay. We look at the direction of motion, which direction is it going in. We look at the rate of motion or the rate in change in motion velocity or the rate at which it moves, okay. So for instance, acceleration is a rate of change in velocity. So when the runner's first taking off, they accelerate, they change their velocity until, of course, they reach top speed and then have to decelerate. So those are all things that we look at with motion. Now we're going to move on to the study of kinetics and discuss. And that kind of looks more again at kinematics, okay, which we talked about in the previous discussion. Now we move on to kinetics. So we said kinematics is describing motion without respect to its forces. Well, we know that forces are involved, particularly when we look at a lot of movements within the body. Just for the body to move, force has to be produced internally by the muscles. So kinetics concerns the forces that cause movement, okay? And there's four primary forces. So again, biomechanics can encompass a lot of different things. We're obviously concerned with biomechanics as it relates primarily to the human body and things that would affect the body. So there's four forces that affect body movement. So if we look at this picture, okay, and this is going to be something that I'm going to bring up in class again. So be prepared for this. There's four forces that affect body movement. So just looking at this picture, I want you to think about what are the forces? What are four forces present here that are going to affect how the woman in the picture is able to move the weight? Okay. So think about that for a little bit. I'm gonna talk about that when we meet in class. But I'd be curious to see if you guys can kind of put that together. Okay, it's not an official homework per se, but I want you to think about that. And then we're also going to look at the concept, because when we're talking about this, the idea of mass versus weight. Now, we tend to kind of just say, well, whatever something weighs in mass, it's the same thing. They're actually two different things. Okay. So mass is the amount of matter in an object, whereas weight is the force of gravity acting on it. Okay? And it's just important to point out, so the U.S. measurement for mass, so when you hear kilograms, kilograms is mass. The U.S. measurement for mass is the slug. Okay? Whereas the metric for force, so in force, or we talk about weight, the metric for force or the unit for force in the metric system is the Newton, okay? So what commonly you hear about is kilograms versus pounds. Those are actually not only are they two different units, but they're two different measurements, because kilograms refers to mass, okay? So again, it's just important to be able to differentiate those. I'm not going to have you do conversions or anything like that. That's going to be something that you do run into, particularly if you do studies. You have to be able to convert. So make sure that, you're able to do that when that time comes. Just for now, know what those different units are as it relates to mass and weight. Okay, so we look at moments and force. And again, these get to all be things that are very important from both a rehabilitation standpoint and a performance standpoint. And again, there's always that kind of mixture where those two come together, obviously, when you're rehabilitating somebody who's physically active or an athlete. So when we talk about moment, we're going to start with that concept first. So if we kind of look over here, we see this little equation, m equals d times f. So this is moment. The moment is equal to the distance times with the force. So basically a moment is when a force acts at a distance from a point of motion. So if we look at this picture right here, okay, we see we have an ankle weight out here. Now, even if we didn't have an ankle weight, we would still have the weight of the leg, okay, acting as a force. But here we're looking at the weight, obviously adding to that. So what we look at, there's a moment being produced here. So when the force acts at a distance, so it's acting at a distance to a point of motion. So where's the point of motion? The point of motion is right here. It's at the hip, okay? So the way we would actually measure that moment is we would measure the distance and multiply it by the force, which would be, in this case, the ankle weight, okay? That would tell us basically how much, we could look at how much stress or how difficult it is for, in this case, the hip flexors to produce hip flexion. Now, one of the ways you could modify this is you shorten the force arm. So if you look down here, with a little bit of bend in the knee, now what have we done to the distance? We've shortened it, okay? So we've shortened the distance, and this is something that when you look at strengthening, particularly in rehabilitation, because you have to modify things, particularly when somebody's coming back from an injury. So you have to be thinking about these things when you're going to apply resistance and cause a joint to have to move through resistance. Over here, we look at the concept of force. So we know force is something that goes on here. Well, what is force? Force is equal to mass times acceleration. So the force of an object is equal to its mass times the rate at which it's accelerating. And this is an important thing when you're looking at, again, kind of athletic performance variables for individuals, okay? So for instance, when, you could measure how much force is going on and there's a great amount of force. If this shot putter was to be holding a wiffle ball, okay, he would not be able to apply as much force behind the wiffle ball. Why? Because the wiffle ball is too light. When he'd go to throw it, it would be too light. His arm would move too fast, so he wouldn't be able to apply as much force behind it. Okay, so force is a combination of magnitude and rate of change, or the speed of an object. Okay, so those are important concepts to look at. And this is kind of what the bulk of this discussion is going to be looking at, all of these different variables that relate to force and how they can affect the body and in what ways, whether they be internal forces like things that affect the muscles or external forces in the environment that the body kind of has to address. So we're going to look at Newton's laws. So everybody by now, at some point, whether, it may not even have been, may have been in high school, elementary school, everyone's run into the concept of Newton's laws, okay? So Newton's laws, the first law is the law of inertia. So what the first law states is that an object at rest or in motion will remain at rest or in motion unless acted on by an outside force. The other part of that is that force is required to start a motion, change direction or speed of a motion, and to stop motion. So that's kind of the law of inertia kind of all wrapped up. Now, there's two things that, with all these laws, there's going to be kind of variables that affect it. In the case of the law of inertia, obviously inertia is one of the variables. So inertia is essentially an object's resistance to being moved or stopped from moving, okay? So again, it's just like the law states, if it's at rest, it will remain at rest. In motion, it will remain in motion. And the actual object's inertia is its resistance to that, okay? The other the other variable here is velocity, so the speed and direction in which an object is moving, okay? So again, I put these pictures in with these as a way to illustrate this. So if you look at this picture, okay, in the strongman contest, this gentleman is trying to move this monster truck. Well, that monster truck has a lot of inertia to it, okay? So that means it's going to take a lot of force to move that truck. And then once it gets moving, it's going to take a good amount of force to stop it, okay? So that truck, we would say, possesses a pretty large amount of inertia, okay? So that's Newton's first law. The second law is the law of acceleration. So the acceleration of a body is proportionate to the magnitude of the net forces acting on it and inversely proportional to the mass of the body, okay? So when we look, so just think of that definition, and I'll state it again. The acceleration of a body is proportionate to the magnitude of the net forces acting on it and inversely proportional to the mass of the body. So that basically means that something is going to move as fast as the forces acting on it, okay? And it's going to be inversely proportional to the mass. So obviously a larger object will likely move slower in most instances, okay? So, you know, kind of similar to the first law, basically what this is saying is that a greater force is required to move or stop, or in that case, stop a large, an object of large mass from moving versus a small one. So the three variables here are force, mass, and acceleration. So if we just look at a deadlift, okay, you know, with a deadlift, if you're lifting a heavy amount of weight, greater force is required to move it. Whereas with a lighter weight, not as much force would be required. A lighter weight's going to move faster, okay, when you go to lift it. So, you know, if in the picture, so in the picture, the guy doing the deadlift, all right, if that's his max weight, which it is because it's a picture taken from a powerlifting meet, okay, that weight is going to move when you're looking at it, the velocity of that barbell is going to be moving relatively slow. Now, if you were to take 70% of that and still put the same amount of force behind it, what's going to happen to the barbell? The barbell is going to move faster, okay? So again, it's related to the amount of forces acting on it and the mass of the body. So the more force, the faster something will move. However, it's also inversely proportional to the mass of the object, okay? So he's trying to pull that weight as hard as he can, regardless whether he's using that weight or 70% of it. The difference is going to be the weight that 70% is going to move faster because the mass isn't as great. So that's your second law, the law of acceleration. And it's important to note, so while, again, people tend to, in application, sort of mix up the first and second laws, they sound very similar, but the way they're applied, there is some differences, okay? So you have to make sure that you're understanding when you're talking about inertia and how that affects something versus acceleration, because they're not the same. They in some ways sound similar, but the overall way in which they're applied, you're going to have some differences there. Okay, then we have Newton's third law, which is the law of action-reaction. For every action, there's an equal and opposite reaction. So if you look in the picture here, you notice the surface this guy is running on. So if we were to compare this surface to, say, a surface like, you know, just like pavement or something of that nature, what would be the difference? Well, when you'd be running on a harder or more stable surface, you would see that the force pressing up would be greater, whereas here you have give. Okay, so you're able to impart more force on that surface, and therefore the surface is able to impart more surface back on you. So that's what we're talking about, particularly in relation to the body. We look at ground reaction forces. So ground reaction forces are probably the biggest thing we deal with when we're talking about the third law, as it relates to the body and performance and things of that nature. You know, when you run, when you jump, you impart force on the ground, and in reverse to that, the ground imparts force back on you, and we have to account for that stress. that's why it's so important that when you talk about whether it's returning to activity from an injury or just even progressions for performance purposes, that you're aware of exercise progression, because of the fact that, particularly as it relates to running, jumping, things of that nature, you have to account for those forces. Okay, so that's something that would come into play when we're talking about the third law. Okay, so moving on from that, looking at force vectors. Okay, so if you remember from the movie Despicable Me, the villain Vector. Okay, so he changed his name to Vector because he committed crimes with direction and magnitude. Okay, so what does that have to do with forces? Well, a vector has both magnitude and direction, so there was something to the name. Okay, so force vectors have both magnitude and direction. So if something has magnitude only, that's considered a scalar measure. So, just to kind of show examples of that, velocity is considered a vector measurement, whereas speed is just considered scalar, because speed strictly just looks at magnitude. When we're talking about vectors, we're also looking at direction. Okay. So the location on space is represented by a rectangular coordinate system. So this is something you'll see in your book. And, we're going to kind of talk about resolving or coming up with resultant vectors. So anytime you have a combination of forces, which in a lot of instances you do, you end up having what's called a resultant vector. So basically, based upon the magnitude and direction of those multiple forces, you end up with a resultant vector. So you would basically look at the two forces, look at how much direction, how much magnitude, and then you could kind of determine what the resultant vector is going to be. So in other words, will there be just added force going in one direction, or will, based upon where the two vectors act on, where there'll be another kind of resultant vector going in a different direction? And we're going to kind of discuss this over the course of the next couple slides so you can see how this is applied. Okay, so when we look at vectors, so if we just look at this picture, so both of these arrows are representative of a vector. Okay, so when you're representing vectors, okay, so obviously we know it has magnitude and direction. So we can see the direction because we can see where they're pointing. Obviously, vector A has greater magnitude. Why? Because the line's longer. So this is there's the magnitude of the force is greater with A. They're both going in the same direction, but the magnitude is better. Now let's say both of these forces are kind of acting together. This is where we say we resolve forces. So how would we resolve that? Well, when they're acting in the same direction, it's easy to resolve. All you got to do is put the tip of one to the tail of the other, and you have a resultant force. So if these two forces are acting in some type of action, okay, they're just generic representative forces. But if they were acting together, you just put the tip of one to the tail of the other, there's your resultant force. Here's an example as to where you would apply this in real life. If we were to look at how much force, if we were to look at, so this leg hanging over the end of the table with a weight on it, okay? So what we would do is we would just, we have the body weight, we have the length of the limb, and we have the downward force of the weight. So all you would essentially do is, they're all acting in the same direction, you just add them all up, okay? Is basically how you do this. Now, we're not going to get into like math and stuff like that. I'm not going to have you go through all that. But what I do want you to understand is that how you would generally resolve vectors based upon their direction and magnitude, and how you'd kind of put them together. Okay, so in this instance, you have, again, you go tip to tail, you get your resultant force. So anytime they act along parallel lines, all you do is you add them together. Now we'll come back to, so this is when they're acting parallel together. When we kind of look at them kind of acting at the same point, but from different directions, and they're not parallel, we'll discuss how you resolve those. And again, I'm not going to make you do the trigonometry and everything to do that, so you don't have to worry about that. I'm just more concerned that you can resolve them graphically based upon the lines. So before we get into looking at vectors kind of acting from the same point but from different directions. We're first going to look at levers, okay? And this is something that we've looked at in previous classes. So a lever is basically a rigid bar that rotates around an axis, and our body's joints are actually represented by levers, okay? But here's how we kind of represent them. Now we have three different levels. We have a first class, a second class, and a third class. And what it's based upon is where the axis is relative to the force and the resistance, okay? So if you were in the 240 class, this should all sound very familiar because we went over this, okay? So in the case of a first class lever, the axis is in between the force arm and the resistance arm. Remember, when you're measuring the force arm and resistance arm, you measure from the distal end. So in the case here where the force is, you measure it to the axis. Where the resistance is, you start there and measure it relative to the axis. In the case of a first class lever, typically the role of a first class lever is usually for balance. Now, based upon the position of the axis can potentially favor the force arm or the resistance arm. So you can actually gain what's called mechanical advantage or lose it based upon how far away the axis is from the force and the resistance, meaning the axis can move closer to the force arm, the axis can move closer to the resistance arm. It's still a first-class lever because it's in between, but you could gain or lose mechanical advantage based upon that. Now we look at the second-class lever here. So we look here, the force arm, here's the force, there's the axis. The resistance arm goes from here to here. So a second-class lever favors force production. Okay, why? Because the force arm is longer. Now, what that does is it functions at the expense at the motion. So for instance, if this is a real heavy resistance here, and you're picking it up over here, you'll have the ability and a greater ability to pick it up. However, it's not going to move very far. Okay, so the second class lever will favor force at the expense of the ability to move the resistance. Okay, or let me phrase that differently. Will favor it over over how much motion takes place at the resistance. So yes, you'll be able to move it, but relatively speaking, the movement's not going to be that great. If we come here to the third class lever, now we see the resistance arm has increased, okay? The force arm has shortened. So here you lose force, but you gain motion. So in other words, if you produce enough force to move this, okay? So say you have your resistance here, but let's say you're strong enough and you produce enough force, that resistance is going to move a lot more, okay? Because it has a longer arm, so it's going to move a much greater distance. Okay, but you lose the mechanical advantage of force because now the force arm is much shorter. Okay, now again, this comes into play in a lot of different things in our life. Our body is comprised of levers. So I want you to think about what do you think is the most common lever in the body? Now, before you answer that question, think about what our body is really meant to do. Okay? So this will be something that, again, we bring up in class. But think about, and most of you know this answer, because, again, I know I talked about it in the 240 class. But think about, if you haven't yet, just think about for a minute what our joints are really meant to do. Okay, so so I said we use levers to determine mechanical advantage. And mechanical advantage is pretty simple to determine. You just take the length of the force arm, you divide it by the length of the resistance arm, and that tells you whether you have a mechanical advantage. If you have a class 2 lever, your mechanical advantage is always going to be greater than 1. If you have a class 3, it's always going to be less than 1 because of the fact that the length of the resistance arm is always going to be longer. Okay, so that's an important thing to note. With a first class lever, it could go either way. Just depending upon how far away, depending upon where the axis is placed. Okay, so again, what does this mean as far as our different classes of levers are concerned? Well, again, it depends upon what their function is. If you look at this picture, So what type of lever do you think a wheelbarrow consists of? So look at the wheelbarrow and just think about it for a minute. What do you think, what class lever is it? So if you said or came up with the idea that it is a second class lever, you are correct. Okay, where's your force? Your force is applied here. Your resistance is here. Here's your axis. So your force arm goes from here to here. Your resistance arm goes from here to here. So when you pick up, now, yes, you say, well, geez, but we move things distances with a wheelbarrow, and you just said that it's not meant for movement. But again, you're not, the fact that you're looking at isn't moving at a distance. You're just looking at picking it up, okay? Which when you pick something up in a wheelbarrow, you don't pick it up a lot. It only comes a couple inches up off the ground, but you're able to do it. You'll stack a ton of stuff in here that maybe you couldn't pick up and carry easily. You know, if you were to put it in other words, what you would put in your arms, you wouldn't necessarily, you know, you wouldn't be able to put in your arms what you put in a wheelbarrow, okay? Meaning that you pick it up and then obviously you carry it, but it's the distance we're looking at is how far it gets picked up here. So that's what we look at when we look at mechanical advantage. So the mechanical advantage of a wheelbarrow is always greater than 1 because of the length of the force arm and the resistance arm. So now we move on to the concept of static equilibrium, okay? So again, we talk about static equilibrium, we look at kind of, you know, particularly for our bodies, we look at our ability to maintain balance. So again, we still look at the concept of force equals mass times acceleration. Now, you know, force is equal to all the forces acting on the body. And in this case, if we're standing still, we're talking static equilibrium, we're standing still, acceleration is 0. So we're looking at basically just being able to, you know, maintain balance, maintain that equilibrium. So when, you know, when a body or segment is not moving, we have static equilibrium, okay? So in order to stand without falling, if you look at this, you can kind of see a little lever being formed here. In order to stand without falling, you need contraction from the gastrocnemius, because if you look at the line of gravity, how it's pulling, if our gastrocnemius didn't contract, what would happen? We would fall forward. So here's your joint axis. Here's where the force of the gastrocnemius, if we don't have this upward force or line of pull from the gastrocnemius, gravity would pull us forward, okay? Now, what's going to happen is muscles, and again, this is another, just again, we look at all the different things that kind of act on the body. Muscles create a compressive force. So don't just think of the weight of the body when we look at compressive forces. Think of the forces that muscles are putting on our body when we're, you know, when we're encountering the ground, whether it be standing still or even if we were moving, we still have those compressive forces. Okay, so the idea of torque, again, we talk about the body and joint movement. So torque is when force is applied around an axis. So when we start to look at rotary motion, we already talked about the concept of the moment arm, okay? So joints produce torque, okay? So again, we look at the idea, so torque is equal to force times distance, much like we talked about with moment arm, okay? So if we look at all three of these pictures, so the important thing to note, it's the perpendicular distance from the joint, okay? So in other words, when we're measuring the distance aspect of this, we're measuring, so here's the joint, we're measuring the perpendicular. So this isn't the distance we're measuring this. So if we were to look at all three of these pictures, okay, the one that's producing the most torque is the one in the middle. Why? Because it's the greatest distance from the joint. Now, the nice thing about our bodies is that this is also the point at which the muscle, in this case, if we're particularly looking at the deltoid, is at its greatest distance from the joint as far as the insertion point is concerned. So at that point, the deltoid's actually in the greatest place to produce force. Okay, so while this will produce the greatest amount of torque at the joint, the muscle's in a good place to where it could produce the most contractile force. So that's kind of the nice thing about our bodies, is that when we look in a lot of these circumstances, that's where the greatest amount of force can actually take place. So again, we look at parallel force systems. So this comes back to the whole concept of force vectors and kind of how they kind of work. Again, when they act parallel to each other, you just add them together. Now, if they're working in different directions, you're still adding them, but then you have to think positive and negative. So if we look at this picture and we're resolving this to find out, well, what's the resultant force going to be? Okay, so you have the force coming from the muscle force, you have the joint force, you have the weight of the forearm, because remember, even though here's the weight and we think, well, we're just lifting this weight, well, the arm also has weight to it too. So we're estimating that the weight of this person's ulna and radius is about 3 pounds, and this is 10 pounds here. So basically what you would do is add all them up, and just depending upon how much force is able to be produced would dictate whether or not you're able to lift this weight. The important thing to note is that in this case, if you think about this just being a 10-pound weight, the point this is trying to illustrate is that the elbow flexors actually need to produce much more force than 10 pounds to lift that weight. You know, the weight that the force that the bicep would actually have to produce would actually be upwards to, you know, 68, 69 pounds in order to lift that. The reason being is because of the torque that is getting placed at the elbow joint. Okay, so that's an important thing to know. So anytime forces are acting parallel to one another, you would add them up. Okay, again, you might have to be plus or minus depending upon whether you're talking upward or downward. In the case of this, you know, that's part of the reason why you would need much more force than just 10 pounds. So in other words, you need more than 10 pounds of force to lift a 10-pound weight. You actually need much more than that. So again, when we're resolving forces, if they're parallel to each other, all you simply do is add them together. Now, if they're coming from the same point and acting at angles, you then have to resolve vectors, okay? And in this case, what a lot of times is you'll make a what's called a parallelogram. That's the shape that you're looking at here. This is a parallelogram, okay? So, and again, these are going to be made up of 2 or more component vectors. So if you look at this picture over here, and I'll show you an example, and over on the other side, we have an example of how this works in the body with the muscles working together. You have force A, you have force B. They're just forces. It doesn't matter where they're coming from. They're just in there. So if you have these forces, they're acting at the same point. Okay, so you have to figure out, well, what's going to be the result of that force? So all you simply do is you make a line parallel to force B, a line parallel to force A, and draw the resultant force out. Okay, so no matter what direction these would be in, you would always be able to figure out what the resultant force is. Here you see an example of this in the body. Okay, so you have the upper trap, okay, and you have the middle trap kind of showing how they produce the resultant force to kind of retract the shoulder. Okay, or the lower trap rather. Okay, the upper and lower trap, and how that works to retract the shoulder. Okay, so you have a force coming here, there's your resultant force. And ideally that's balanced to the point where you could perform shoulder retraction in that manner. So this is important when you're talking about muscles, particularly muscles with multiple insertion points, how they actually will kind of act when they start to produce force. Okay, so forces acting at angles. So, and that's what we're dealing with a lot of times, particularly as it relates to the body. So we have, that's what's called, we're calling this a concurrent force system. So if a vector is producing forces perpendicular to the body segment, it's going to be purely rotational. Okay, and again, we're talking joint motions. We're always talking about rotational forces. So with force vectors, you're going to have 2 different types of forces. You're always going to have the normal force, which is the rotational force. So obviously the whole goal of muscles is to produce rotation when we're talking about joint motion. But then you also have what are called tangential forces. And those are compression or distraction forces. So at joints, you're always going to have your normal forces and your tangential forces. Your normal forces are trying to rotate the joint. The tangential forces are trying to either compress or distract the joint. What's going to determine which force is the more predominant force is based upon the based upon the position of the joint. Okay, so, and ideally, when we talk about our joints, when we have the greatest distance or the vector producing force is perpendicular to the body segment, everything's going to be rotational. So if you remember going back to the picture, I'll show you it on here, but remember going back to the torque when I showed the 3 different positions of the shoulder going through shoulder flexion. When the shoulder was at 90 degrees moving up, that's when all of the forces were strictly being put towards rotation. And the reason for that is the muscle has the greatest distance from the joint. The insertional point of the muscle is the greatest distance from the joint, ergo it's able to produce the more force. You see that in this picture as well. The elbow is one of the easier joints to see this in. So when the elbow is at 90 degrees, okay, if we look here at the bicep, okay, the resultant force vector is only going to, from the bicep, is strictly going to be rotation. Why? Because its distance is you have a perfect perpendicular angle being formed, and its distance from the joint is at its greatest. So at a 90-degree angle, everything's being directed towards rotation. Now, if the elbow was only flexed, say, 30 degrees, so if it was kind of coming down here, then there would still be rotational forces taking place, but they wouldn't be the only forces. You would now have some compression forces taking place because not all of the force would be being produced towards rotation. Okay? So you have 2 forces, the normal force, which is the rotational force, and the tangential forces, which are either compression or distraction forces. Okay, so looking at other forces acting on the body. So there's some situations where we need to reduce load on the joints from an exercise perspective. One of the best ways to do that is either through what we call gravity eliminated positions. So there's actually positions where we could eliminate gravity with resistance exercise, or we could put them in water. Okay, so when we look at water and we look at Archimedes' principle, it looks at the impact of fluids. Now, fluid can be either air or liquid. In the case here, when we're talking aquatics, we're obviously talking about liquid. So Archimedes' principle looks at the concept of buoyancy. So when a body is submerged in a liquid, it is kind of lifted up or buoyed up by a force equal to the weight of the liquid that gets displaced. So in other words, when you go in water, you displace liquid. In that case, you're going to have an upward force placed at you. So, where this is easiest to see is over here in this picture. So now she's in shallow water here, so she's not floating. I mean, here obviously, she's floating. There's no stress. There's obviously no weight bearing here. But you'd see something like this. So underwater treadmills are very popular. I was fortunate enough to work somewhere where I had an underwater treadmill for a while, but what you basically do with the underwater treadmill is based upon how much weight bearing you want them to have, you just have them go higher water. So the higher the water, the less weight they bear. Okay, so obviously there's no water here. It's 100% weight bearing. Here you look at water at about, just at or maybe slightly below waist level. It's about 40%. Here, you're a little bit higher. It's about 50. I'd probably say it's even a little more than 50%. Obviously, if you go all the way up to the neck, you're at almost, you're only bearing probably about 10% of your weight if you're up at the neck. But the higher the water, the more, because basically what essentially is happening is you're displacing fluid. So the role of that fluid getting displaced is going to push you back up. Okay. It's the same thing when you're, so here you have this, here you have some assistance coming from the water, and it could also provide some resistance as well. Obviously, we know flotation devices kind of assist with that as well, and you can do exercise with that. But these would be situations where you want to, again, try to reduce impact on the joints. Again, fluid could be either air or liquid. We tend to think of fluid as just being liquid, but air is technically a fluid as well. So the concept of fluid flow. Okay, so this allows fluid to move and also regulates your motion. So you have 2 different types of fluid flow. You have laminar and you have turbulent. So if you look here, this is a laminar flow. This actually can speed up movement. So if you look at this, what you have is laminar flow, and you have this nice even kind of movement of the liquid over the object. Whereas when the object is kind of placed where it's going to have more surface contact, you get turbulent flow, and it produces what are called eddy currents. Okay, so if you look here, this actually produces greater resistance because of the position here. The greater surface mass that's going to be in contact with the fluid and the movement, it produces this eddy current. So this is all resistance. Okay, so think about just moving your think of moving your hand in water. Okay, if you were just to kind of lay, pronate your forearm and kind of lay your hand flat and move it through the water, you can move it through relatively fast. Whereas if you were to kind of put it in a neutral position with your thumb up and run it through the water, it's a lot harder because now you're creating those eddy currents and resistance. So we can modify. It's when you start to get into things like looking at rehabilitation in the water and things like that, you can modify, make things harder or easier just based upon limb position. So fluid and resistance. So again, the concept of lift and drag. With flight, we look at aerodynamics. With swimmers, we look at hydrodynamics. So, if we look at flight, if you remember the concept of Bernoulli's principle, so the shape of a wing, okay? So when a wing is moving through air, there's downward pressure exerted by the faster moving air. Here you have pressure being slower because it doesn't have to move over as great a distance. So this air here up top has to move over a much greater distance, ergo it's going to move very fast. Whereas the air underneath here is moving much slower. What that means is that's where you get that lift from in a wing, because the air coming underneath has to move slower. When we talk about hydrodynamics, if you think about what swimmers do, okay, they wear the swim caps, they shave all the hair off of their body to basically allow their body to have the least amount of resistance moving through the water as possible.